So both of these are implementations of a sum of products. And in fact, the same sum of products we've been dealing with. One is a NAND-NAND tree, and the other is a NOR-NOR tree. You can see the NOR-NOR tree actually involves a lot more inversions. But let's work through, using De Morgan's law, why this is actually equivalent to the sum of products we've seen earlier. And so I'm going to use this notion that a NAND, okay, converts into an OR of knots. So a knot of AND, see what I did is I redrew that symbol. You can see the little animation there as I change it from a bubble on the output to a bubble on the inputs. And as I do that, as the bubble passes through the body, it converts ANDs to ORs and ORs to ANDs. Okay, so if I take this diagram over here, you can see what I've done is I've redrawn that 3-input NAND gate as a 3-input OR gate with inverting inputs using De Morgan's law. And then I notice I can match up these bubbles. An inversion on the output and an inversion on the input sort of goes away. And now you can see I have my sum of products representation here, but I've built it out of NAND to NAND. So it turns out that if you're dealing with sum of products, you can do it all with very simple inverting logic, NAND-NAND. The same thing is true of the NORs. It seems a little bit more cumbersome to do all this redrawing. And you look at this and you say, well, why would I ever do NOR-NOR? So let me turn this problem over to the collective wisdom of you as budding engineers. Okay, why might I prefer the bottom diagram? You have to think a little bit outside the box to think about why the bottom diagram might be more interesting. Not 100% obvious, but you know, if you were pressed for an answer under threat of having the logarithms come in and sing to you and said, wait, I'll come up with an answer, really. So, you know, what would you do? What would you say? What are some possible advantages of the bottom one? Yes, sir?
Maybe the NOR gate is easier to build or less expensive.
Maybe the NOR gate is easier to build or less expensive. And so the answer is NANDs and NORs actually turn out to have exactly the same number of FETs in them. So that's a good idea. You're sort of on the right track. Yeah? NORs are faster. Well, it depends a little bit on the relative strengths of N's and P's and things like that. But typically each one is fast in one direction and slower than the other one because they have a parallel switches and one for pull up or pull down, and then series switches, and the series ones tend to be a little slower. Okay, but there is something about fast and slow. Yes, sir?
The final inverter kind of lets you control when the output is released.
Yeah, so the idea here is that, you know, notice that to just charge and discharge this output node in this diagram, I have all the FETs. You know, in this case, the pull-down chain for the NAND gate. So all that current has to flow through this little stack or 3 FETs. Here, inverters can be made very fast, okay, because there's only a single FET in the pull-down chain and a single FET in the pull-up chain. And in fact, I can make them wide FETs. And so what I have is the ability to drive very heavily loaded signals with a lot of capacitance. I can make them switch faster. So this idea of buffering in a single signal, a heavily loaded signal, a signal that goes to lots of other inputs, with an inverter is attractive because that way I can make that signal change more quickly by changing the dimensions of the single FETs of the inverter. And so this notion of buffering, here what I'm doing is, you look over here, it's a little easier to see. Here, A is connected to a pair of FETs. Over here, it was actually connected to, you know, these inputs get connected to a lot of different signals. So buffering is something that, you know, is worth keeping in mind. So there are times when, you know, this slightly more complicated circuit would actually operate more quickly.